So hi everyone. Like Ray said, I'm Chris Weber. I work with Casaba Security. It's a company I started about 8 years ago. We're a software security testing and product company. And we've really turned focus a lot to globalization and Unicode in the past couple years because it's just ripe and rich with vulnerabilities. And I see lots of work to do there. So what's this talk about? Going to go into visual spoofing, and I call them counterfeiting attacks, and also I'm going to cover some text transformation attacks. Now, why should you care about this? Well, let's look at the visual spoofing. If you look around, I mean, ever since we were kids growing up, branding has been really important, right? Identity has been important. All this stuff that identifies people, companies, places, to us, it's text, but it's visual. We rely on seeing something visually to know what it is and to trust what it is. Now, with the cloud and cloud computing being the big topic today, one thing I don't hear many people talking about is what's also central to the cloud is text. I mean, we deal with text every day. That's what most of us are doing on our laptops all the time. Unicode is a way of handling text. And I'm going to get into a little bit about the background of that. Another thing you're going to learn here is some new techniques for finding bugs. Clever ways to get cross-site scripting attacks, past filters, or into web applications, and also some good test cases for fuzzers. And I'm trying to scroll with the scroll wheel. Sorry about that. It's flashing a little bit. So I wanted to get some tool announcements out of the way rather than try to save them for last, because like Ray said, I do have a lot, so I may spill over into lunch a little bit, but I'll try not to. We have an open source tool called Watcher that was released that is a web application testing tool, and the URL for it is right here, and it also covers some of these Unicode cases. So I wanted to point that out if you want to go grab that and run it against your web applications. It's a passive tool, so it's really easy to use. There's another tool that we've been working on that I was hoping to get ready for release, but at least have a demo of it. I call it the Unibomber, because basically we look at a web application and we just bomb it with all sorts of characters that we know transform in certain conditions to malicious characters. So what you end up getting is when you're testing web apps looking for cross-site scripting bugs, you want to know, is the input that I provide going to be encoded on output? Is it going to be stripped, removed, replaced, all these sort of things? So what the Unibomber does is it injects inputs and then it looks at all the outputs to see if that was properly encoded or if you have a dangerous transformation somewhere. So, visual spoofing. Can anyone tell the difference between these two URLs? Right, they both look like Google.com. Now I'm picking on a couple browsers here, admittedly. Now can you tell the difference? Now it's pretty obvious. This isn't Google.com. In a minute I'm going to let you actually click on some links. If you have your laptops, you can bring them up and I'll show you some real test cases that you can click on to sort of see these live. So this is moving on to the other portion of the talk, talking about the transformers and characters that transform to dangerous inputs. Here's a case of something I'm going to talk about where a special character transforms into something dangerous. Okay, so what's the real agenda here? So, quick outline. I'm going to give a quick crash course on Unicode. How many people here develop globalized software? Can anybody raise their hand if you work on the development side? And how many people test globalized software? And I'm not going to ask who uses globalized software because everybody would raise their hand for that. So after we go through a quick crash course, I'm going to go through some of the root causes for the security vulnerabilities associated with Unicode and some of the attack vectors for exploiting them. And if we have time, I'll do some demos of the tools that I mentioned. So on to the crash course. So what is Unicode? Unicode enables globalization in software. It enables us to transmit and store text in one framework. And when I say text, I'm talking about all of the world's languages and all the world's written scripts can be stored and represented using Unicode. In one sense, Unicode's a large database. Now, the attack surface of Unicode is pretty big. At the core, almost all software uses it. All programming languages, operating systems, web applications, and like I mentioned, the cloud. So all users, in a sense, are affected by these attacks. Now, how many people think Unicode is a 2-byte character? Because if you do, just stop thinking that. That'll get you in a lot of trouble. Unicode it's a very large and complex standard. Okay, if you pick up the book, you might hurt yourself. It's about 1,500 pages, I think, on the last iteration. So we're talking about a lot of things buried inside this standard. Now, it used to be, when dealing with text in different languages, that we'd use code pages and character sets like Shift-JIS, for Japanese, or GB2312 for Chinese. There's ISCII characters sets. Then there's the traditional Windows character sets, 1252. There's a lot of history to character encodings and character sets. Around 1990, Unicode became official, and when everybody realized that there was just a huge mess of text interoperation, and some smart people started to realize that we just need a single framework to represent all the world's text. Unicode came out at the same time an ISO standard came out that was set up to do the same thing. Unicode has since pretty much taken over and is the de facto standard for text representation. Now, in Unicode, the ASCII range has always been preserved because it's very special. So they made every attempt to keep it intact. Once you get above 0x7f, and then it's Unicode's territory. So the current standard is at 5.1, and we use a 21-bit scalar value to represent characters. They were really called code points. Every character has a unique number associated with it, and this is the range, and it's also the notation. The standard Unicode notation is U plus, and then some hex number to represent the character's place in the mapping. So let's take a closer look. So here's the Latin capital letter A, which most people know is 0x41 traditionally. In Unicode, it's U plus 0041. And if you start to take a closer look at this character, you'll see that the database associates a lot of metadata with every character, right? So on the left, I've got some of the categories that are assigned to this, letter, uppercase. The interesting ones for me and for testers are the 2 lower, 2 upper mappings, the normalization mappings, and also the binary properties. Well, with the capital A, it's not too interesting. But if you look at another character, like the Latin small letter, long S, has some pretty interesting properties associated with it. Now, this character is well out of the ASCII range. It's still considered a Latin class of character. When it's uppercased, however, this character actually transforms into an uppercase Latin S, which is pretty interesting. And if it's mapped through different normalization mappings, it'll actually transform into a lower letter S. Now, I'm going to wrap up the Unicode crash course by talking about encodings, because that's obviously a really important part of what's going on. How do you transmit and how do you store text? The Unicode has 3 primary transformation formats, the UTF, Unicode transformation formats, 8-bit, 16-bit, and 32-bit. There used to be a 7-bit. I think there was even a 6-bit at one point. Those have been deprecated. And UTF-8 is pretty popular. It's pretty much the encoding of the web. So you see it everywhere. UTF-16 is pretty popular for programming languages and operating systems. They use UTF-16 at the core. Now, both UTF-8 and 16 are called variable width encodings because they can represent a character in anywhere from 1 to 4 bytes. UTF-32 is awesome. Like, if we could just use that, we'd be set, because it's just a 1-to-1 mapping. There's no algorithms involved. It's just a straight representation of the code point. Now, another interesting area when you're testing Unicode-enabled software is escaping mechanisms, right? And how do characters get escaped? The first, so look at this character here. This is the full width Latin capital letter A. And these are the different ways to represent it using different escapings. So the first is the URL encoded, which you'll see on your browser's URL bar and in a lot of other places. And then the next two are the numerical character references. And they can be either the hex or the decimal. And then following that, sometimes you see just raw byte escaping mechanisms like in JavaScript and lots of programming languages. And then there's the \U notation, which is supposed to represent the code point. And when you start to look at software, like MySQL and a lot of other software, you'll see that you can't really go much beyond \U FFFF, even though Unicode is much greater than that. A lot of software implemented early standards of Unicode and pretty much limited it to FFFF as the top, the ceiling for what they'd support. So you don't actually get full support for all Unicode in a lot of software. Okay, so I'm going to jump into talking about some of the root causes. So visual spoofing and IDNs, internationalized domain names. So right now Unicode has over 100,000 assigned letters from all the world's languages, past, present, and presumably future. So there's many lookalikes actually within some alphabets and also across the many alphabets. If you want to follow along, you can open up your laptop browser and go to this page, nottrusted.com. I actually own that domain name, so it's kind of trusted. /idn.php. So you can actually click on some of the links, and I recommend using Safari or Firefox or Opera if you have it. So what's the deal here? Some browsers allow internationalized domain names in .com labels to certain extents. So VeriSign has supported internationalized domain names for many years, since about 2001, I believe. And slowly, the software has started implementing support for IDNs along the way. Here's an example of an IDN in a .com label in the Safari browser. And this is a visual spoof, right? You can click on this link and you'll see that this is not Google, even though it looks very much like it. This is it in another browser, Opera. So what's going on here? Why is that allowed? Well, some of the limited support for internationalized domain names has to do with making decisions on languages and making decisions on what character families and alphabets these letters belong to. In this case, the spoof here is the letter G. There's a Latin lookalike for the letter G. Now, how many people here know about the PayPal.com hack from 2005? So this, like Ray said, has been around for a while. In 2005, Eric Johansson actually demoed or released an IDN advisory for PayPal.com where he pulled off a spoof using a similar technique. And I think he actually based some of that work on earlier work from 2001 from some other researchers at a university that were also looking into homograph attacks and lookalikes. So this class of attack has been known for quite some time. The Unicode, the people who create the Unicode standard are very smart people. They've known about this. They saw it coming a mile away. So what's going on and why is this still happening, right? ICANN, the Global Internet Authority, is trying to remedy some of these issues at the policy level, right? So they set standards. And if you take a look at what they're recommending, it's pretty good. They have a deny all default policy for certain labels like .org. I think .com is pretty wide open. And then after they do this whitelist policy, they say, okay, let's limit the scripts. So we can only allow Latin script in the .org label, for example. However, as you saw with that spoof, there's actually characters within the Latin label that look alike. And then they try to actually limit characters, like blacklist characters, and this is at a policy level. So we're definitely not going to allow symbols like slashes and question marks and things like this to appear in domain names, which is all good until you get out of the domain name and into the subdomain level. And once you get into the subdomain level, you can start playing a lot of tricks. So really the problem today seems to be more about a divergent sort of implementation of these standards and these recommendations, right? All the user agents are doing it a little differently. And also the IDNA, which is the RFC standard for internationalized domain names, is fairly old at this point. It's based on Unicode 3.2. I think it came out in 2002. It's actually being updated, so I believe later this year or early in 2010, there's going to be a new standard IDNA that's going to address more of these issues. So at the end of the day, the registrars are still allowing confusables to exist in domain names, and they're unable to control the subdomain labels. Okay, so take a look at some of the non-Unicode attacks. Right, these are like the traditional things. So if you have a letter R and an N together, in some fonts that can look like an M. Right, so here's an example of a couple domain names that look similar. Now, monowidth fonts kind of suffer from this problem too, right? Zeros and capital letter O's can look alike. Ones and L's can look alike. 5 and S can even look alike. Whoops, went backwards, sorry. And then there's the old classic phishing attack, like the long URL to just fill up the URL bar and just confuse users, and they're just going to go there and click on it anyways because they see Facebook somewhere in the domain name. And all that stuff still works today. And then here's sort of the Unicode-based attacks. On the top you have what I was showing you earlier with the demo. Apple.com using a same script, Latin letter, alpha. And then in the middle you have a Facebook spoof that's actually using mixed script. It's actually mixing Latin and Greek together. And then on the bottom you have something that looks like abc.com that's using all Cyrillic. Now, a lot of browsers actually whitelist.org to say that they're going to allow IDNs to be displayed in any .org label, which is a good thing. I mean, really, you don't want to stifle IDN. It's here to stay, and when you start to look around the world, it's more important in a lot of other regions than it might be right here in the United States. So here's another spoof that if you went to that page, you can click on the Mozilla link, and you'll see a domain name that looks just like mozilla.org. So can anybody see the difference between these two? I'm sure somebody can. Yeah. That's it. So this is another way to sort of spoof using characters that are pretty close in variation. I mean, visually, when you look at it at first glance, you're not going to really notice, unless you're keen to seeing acutes over eyes. Here's another attack spoofing with punctuation marks like slashes. Now, this is a full-width solidus that looks like a slash. This character actually normalizes down to a slash, so this attack doesn't really work, even though it used to years ago. So the browsers follow the IDNA standard, which tells them to normalize. The question was, who normalizes those characters? And yeah, so the browsers follow a series of steps, and one of them is normalization to a normalization form that actually decomposes that character. So here's another sort of variation on that kind of syntax spoofing. What happens if you get letters that actually look kind of like punctuation marks? So here's a Japanese character that I'm trying to use to kind of represent a slash. Moving away from IDN, because there's actually more ways and things you can do and tricks, but I didn't have time to fit them all into the turbo talk here. So I want to get into some of the other interesting things you can do. And these are more for fun. These are tricks you can play on your coworkers and stuff, right? So there's some invisible characters in Unicode. And if you look here, I'm not sure if you can, how well you can see that. But right here, Can everybody see that? Those two folders have identical names, my folder. And if you look below, down here in the command shell, you'll see a little box because it's not representing that Unicode character properly. That's actually an invisible character. Here's another example of using BIDI. BIDI is the bidirectional algorithm. It's what tells text to flip from right to left or left to right. And there's actually these override characters in Unicode, which are really cool, because you can stick them into the middle of a text stream, and the text will flip at that point on. So right here you got a file that looks like it ends in a .txt extension when it really ends in a .exe extension. All right, so I'm going to move out of visual spoofing and start getting into some more of these like transformation style attacks. So best fit mappings. While Unicode supports the entire array of the world's languages and scripts, a lot of other character sets don't, and they're really specific to certain regions. So this concept of best fit mappings kind of came into play whenever you're kind of transforming data between character sets or to Unicode. There might not be a one-to-one mapping. If that's the case, then you might just need to come up with like a best fit. So what you have here is like the Greek small letter sigma will become the Latin small letter s when a best fit mapping occurs. You also have another one on the bottom when the prime character becomes an apostrophe. So these are cases where software has to make a choice and decides to just go ahead and fit this character down into something that we can work with. Now, best fit mappings are sort of pervasive. They're different among different vendors. I mean, database vendors, operating system vendors, web apps, everybody can do it a little differently. Oftentimes you find best fit mappings occur in core libraries like .NET or some of the Win32 APIs, in Java, ICU. Basically any major library at some point is going to perform a best fit mapping. Now I have a paper on the CD that is going to talk a little more, goes into more depth about these things. And we're in the middle of doing some studies right now and intending to provide more data about which libraries do perform best fit mappings, so we can kind of call those out and you can be more aware. For example, if you use pinvoke anywhere in your .NET code, by default it actually marshals strings as long pointer strings instead of long pointer wides. So what you get is a situation where a full width letter A will actually map down to an ASCII letter A. So here's a quick example of a social networking system that we were testing and found a pretty cool cross-site scripting bug using best fit mappings. Now, basically they had a really cool cross-site scripting filter, and they also had like this profile editor, which is common on social networks. And you could control some of the cascading style sheets with colors and other things. So they were specifically forbidding the Moz binding attack vector, which I don't think is much of an attack vector anymore since they sort of neutered it to be domain specific. At the time though, you could cross domains with Moz binding, so it was pretty cool. But by inserting a full width character, they would actually best fit map this full width M back to an M on somewhere down the stack of what they were doing. We ended up with an attack that was pretty cool. So normalization, I fit it here as a bucket. It's not really, it can be a root cause. I mean, normalization is actually its own standard. There's a specification for how to normalize. There's actually 4 normalization formats. They each behave a little differently. Some of them canonicalize, some of them don't. Some of them decompose, recompose. And there's a lot of complexities that go into normalization. It's not just normalizing to lowercase or normalizing to uppercase. It's more complex than that. Let's see here. Yeah, so here's an example of where the Latin capital letter I with a dot above will actually become 2 characters when it normalizes under certain forms. So why is this a problem? Well, this could be a problem if you're dealing with buffer sizes, for one thing, because now you've got something that went from being 2 bytes presumably in UTF-8 to being, well, 2 bytes in again, but, or no, sorry, that would be 4 bytes. So you've just doubled the byte count after you normalized. Now, there are dangerous characters for cross-site scripting or web applications. So there are some, and here's an example of one that basically normalizes to the less than symbol. So it can be useful when you're testing for web applications. And this is the type of thing that the tool I was talking about earlier, the Unabomber tool, will actually inject all these characters into the web application to detect these transformations on the fly. So here's an example of how that attack vector would look, right? You're trying to get script in past a filter, and you need to get your angle brackets in. So you use one of these special characters, and lo and behold, it transforms on the outside. So there's this talk about overlong UTF-8. This has been a big issue for many years. Eduardo talked about it yesterday in the XSS talk that they gave. And it actually released a really cool bug on PHP that exploited a combination of an overlong and a signedness issue. That was really pretty cool. Overlong issues go way back. I think the first biggest example of them to hit everywhere was the famous Unicode IIS bug back in 2000. Right? Back then you could do the ... with an overlong sequence of characters. So overlong is basically, with UTF-8, there's a bit distribution matrix, and you can represent characters that are supposed to be single byte characters, like the apostrophe here. You can represent them using more than 1 byte. So here's an example of where the byte structure would be C0A7, but it's an overlong form of the apostrophe. The Unicode standard actually forbids generation of the non-shortest form and also interpretation of it in most cases. So it's a good test case for a lot of software because a lot of software still does support it. I know a lot of the Microsoft software does not support overlong and will actually do what's suggested and throw errors when overlongs are encountered. So for the web app testing community, one of the old staples was ... right? Trying to get directory traversal attacks to work. So how many ways can you say ... Here's a little slide that's kind of messy, but if you want to look back for some test cases, they'll all be here, and this shows you how to do ... with different normalization forms, different encodings, and the overlong sequences as well. So let's talk about handling the unexpected, because there's plenty of unexpected cases. And these are things that are really good for building fuzzers. Definitely suggest using unassigned code points in fuzzers. Also sticking in half a surrogate pair, which I didn't really talk much about, but surrogate pairs are part of the UTF-16 encoding. And then sticking in a lot of code points that have special meaning, like the bomb, which I'm going to talk more about in a minute. There's also this other attack vector called overconsumption. Some people call it swallowing or absorption or eating characters. Unicode actually has a name for it. So I'm just going to stick to the name of overconsumption. So what happens is you get an ill-formed byte sequence because UTF-8 is a multi-byte sequence, which means when you get a character that's 2 bytes long, the lead byte actually tells the parser how many bytes to expect, and the following trailing byte should be a valid byte in a valid range. So what happens if the trailing byte is not a valid byte in the valid range? Then you got an ill-formed sequence. You got this lead byte hanging out here with no trailing byte to follow it. So some software might overconsume the following character, assuming that that's just going to be a part of the sequence, right? Even though it's not supposed to. So here's an example of an attack where the C2 byte and is the valid lead byte indicates to the UTF-8 decoder that there's a trailing byte, but 3E is not a valid trailing byte. So what happens is those 2 bytes get consumed, and what you end up with is the stuff on the other side. Here's a more practical example of how you'd use that in an attack. Here you have an image source with a C2 byte right before a double quote. And now if I'm an attacker, I can control that payload for the image source. Then I can get that double quote to get overconsumed. And then the browser ends up seeing what's on the bottom, which is an on-error event. So another way to handle the unexpected is character substitution. And this is the idea of what do you do with these ill-formed bytes, unassigned code points, half a surrogate pair, and these other situations, right? Well, correcting insecurely would be the idea of replacing or substituting characters like dots or slashes or other characters that might have special meaning, especially within a protocol. So there's another case, sort of like just straight deletion. If you run into those situations, the software might just delete the character or remove it from the stream. Here's an example of a vulnerability that exists in Safari. I think it might have been fixed actually with the other day's big update. So this is an example of where you inject a bomb character. The bomb is the FEFF. Now this is a special character because the bomb, which I'm just going to, well, that's a few slides away, so I'll wait. But so how do you correctly handle these situations? Unicode has a correct replacement character. It's called UFFFD, and that's a safe replacement. A lot of times people use the question mark as well, which can usually be pretty safe, depending. So the attack vectors for these situations are a lot of times to bypass the filters, the web application firewalls, IDSs, and other systems. So here's a closer look at that attack in Apple Safari, and it was also in Firefox. Earlier on it was in Firefox's HTML handling, and then later, at the same time I reported it to Safari, I found it in Mozilla's JavaScript interpreter. So you could stick this bomb character anywhere midstream, and it would basically get ignored or deleted during the parsing routines. So bomb is a special character. It's there to tell the parser what the byte order is. So it's supposed to only occur at the very beginning of a text document, HTML, XML, whatever, and tell the parser that, hey, this is UTF-8 encoded, UTF-16 little endian encoded. But the bomb also carries other special meanings. It's actually in one of the invisibles, and it actually has this default property of being an ignorable. What's that?
What does it mean that it's ignorable?
Well, so the question was, what does it mean to be a default ignorable code point? And really, that's just the metadata that follows this character. So it's up to the software how they might treat that. So different Unicode parsers might handle ignorables differently. They might literally ignore them, which seemed to be the case with this. So then there's a class of attacks around casing operations. And when I say casing, I mean upper and lower casing operations. And the kind of issues you get here are more web application specific XSS attacks, and you also get buffer attacks. So here's a case where that character, a lowercase, becomes an I. Here's another case where the length of X does not necessarily equal the length of X when it's lowercased. One of the general themes for guidance is to perform casing operations and most operations, normalization, before validation, but there's also cases where you might need to perform it validation before you actually deal with these characters too.
My favorite casing thing is this German character that uppercases to two S's.
Yeah. So this is a good lead way into the next topic. He was talking about this German character that actually cases from one character into two. Here's an example of buffer overflows, and basically, I'll just jump to the tables here. So here's the casing table for buffer overflows. These are if you want to just throw some test cases into your fuzzer or whatever you're looking at, throw these three characters in there. The top two will actually expand by a factor of 1.5. And the bottom one will actually expand on uppercase by a factor of 3 times. Normalization kind of has the same scenario, but more significant because you actually get up to 18 times expansion on some characters. So this is a good table of test cases as well. Here's an area I've been trying to play around in more, controlling syntax. So a lot of characters have properties. They may be associated to be white space characters. They may be deemed quotation mark characters by the Unicode sort of database. Now, you might be able to use this in certain HTML parsers or other software that might make decisions on those categories. And here's an example of a bug that I found in Opera that did that, actually. So here's the actual test case. So this special character, 180E, basically acted just like a space character, like a 0x20, right? So this attack actually worked, where you could have, if you can control some payload inside of an attribute, you can control spacing as well. Let's take a look at that character. That's a fun character to use. It's called the Mongolian vowel separator. And it has binary properties and a general category of space. So it actually shows up as white space, and it actually can assume spacing properties in a lot of software. Specifications. So that issue ended up being more related to the HTML specification than anything, because HTML4 left it up to the vendor to implement white space how they wished. They defined, I think, 5 characters in the spec, and they said you can treat other characters as space as you wish. HTML5 changed that, and they became very explicit about only these 3 or 4 characters can be treated as white space. There's also some issues in the other specifications. I took a closer look at why this bomb character in the middle of midstream documents was being ignored, and one of the standards in Unicode actually said, well, you can ignore this character if you encounter it midstream. I thought that was a pretty big issue. It turned out that it was with some software like Safari, and they've actually changed this specification now and removed the verbiage. So it can no longer be ignored. Now you can either error or handle it as a pure character. So, character transformations. This has been kind of the theme. Now there's the idea of, there's a lot of software that wants to mix, accept characters from one character set and be able to transform it into another character set somewhere down the road. This is common in web application that might talk to a database like Oracle or some, when you start having a lot of systems that interoperate. So the problem is that character sets and the mapping tables that go along with them are different across vendors. So Oracle might do it differently than different Linux distributions do it, than Microsoft does it, than Apple does it. They're not well defined, these character sets. So avoid them if possible. And the best thing to do if you do wind up in a situation where you have to transform between character sets is to use Unicode as the broker. And that's kind of the common situation. But there's also this idea of the PUA mappings, the private use areas, that can become problematic when you do that. Character set mismatches. This is the idea of you get a web response, an HTTP response, and the content type in the HTTP response header says one thing, and the meta tag in the body says something else. So then the browser might have to make some decisions on what that content really is. So if you are dealing with web applications and you have some say, definitely force UTF-8 everywhere instead of trying to do specific character set support and character encodings, and error out if you get requests that are violating that. All right, so I think I've almost made it through. So let's just go through real quick. There's the Watcher tool that I mentioned. These are a list of checks that this tool will look for. This is the passive sort of security testing auditing tool that's built as a plugin for the Fiddler debugging proxy. It's a really popular proxy. It allows you to analyze HTTP traffic, intercept it, modify it, do a lot of cool stuff. So we built a plugin for that proxy that basically just runs analysis on all the traffic. So now we can look for things like weak cookies, weak SSL, information disclosure, issues with Flash and Silverlight. We can look for hotspots for cross-site scripting attacks. So we can look at JavaScript code and analyze it. So we can do all this stuff passively. So it's pretty cool and pretty useful. Here's a screenshot of the interface for the reporting interface. And that's the URL if you want to grab that. It is free to use. So there's another tool I wanted to mention that I was going to demo here today, and this is our runtime cross-site scripting testing tool. So this is the one that's real deterministic. We control the payloads. We also control, we can detect based on canaries that we inject. And I'll just bring that up real quick so you can see it here. Okay, so here's a sort of a view. This is Fiddler, kind of on the outside, and this is the Unabomber on the inside. Okay, so we inject a canary so we know what to look for, and then we go ahead and say, all right, auto inject into post parameters, query string URLs, and if we don't know what the data type is, if it's not post, maybe it's SOAP or some other specialized XML format, just if you see your canary, inject into it. And then what happens is, see here. So, sorry, so this is a screen where we have character mappings. And this is where we load our character mapping tables, and we say, all right, these characters transform to these dangerous characters. Some of them aren't so dangerous. Sometimes we just want to prod a system and probe it with valid characters that might not be dangerous, just to see how they are transforming data. So then you go ahead and you open up your browser, and you go to Google, and you type test and search. And then over here, the Fiddler will populate its session list over here. Sorry, on the left. Can't really see it because I've got the Unabomber maximized. And then we'll analyze those sessions, and we'll look for all occurrences of our canary. And we'll try to identify if a transformation occurred or if a proper encoding occurred. So right now, there's no filter to show you just the dangerous stuff, so we're actually looking at all the safe stuff as well as the dangerous stuff. But so that way we get a quick glimpse into, hey, was this payload encoded? Was it transformed in a dangerous way? Or was it just a purely unencoded response? And that's about it. So thanks for coming, and I'll be happy to answer any questions or follow up on anything. Does anyone have any questions right now? Okay, I don't see any questions. Everybody's hungry, ready for lunch. Let's go.